Discussion on operator K. So how to write the three unknown unbalanced voltages? You know VR, Vy, Vb. So what are these three now? These three are unbalanced voltages. How to write them? In terms of zero sequence. Next, positive sequence. And then negative sequence. So here you are having 9 symmetrical components. Now we check how to make this to 3 symmetrical components. So first we have the system phase sequence. Now a three-phase system has two possible phase sequences. What are those two possible phase sequences? You know the phases. We have R, Y, B. If you refer in clockwise direction, R, Y, B. If you refer in anti-clockwise direction, R, B, Y. So a three-phase system has two possible phase sequences, RYB and RBY. So you represent the three-phase sequence here. So VR, Vy, Vb. Here it is 120 degrees. And now we represent firstly the positive sequence network. So positive sequence components. So first we represent positive sequence components. So how about this positive sequence components? They are equal in magnitude and displaced from each other by 120 degrees and with phase sequence same as the phase sequence of the power system network. Same as the phase sequence of power system network. So positive sequence components are equal in magnitude and displaced from each other by 120 degrees with phase sequence same as the phase sequence of power system network. So how to represent now? VR1, Y1, B1. VR1, Vy1, Vb1. So all these are equal in magnitude, displaced from each other by 120 degrees. So how to write this B1 in terms of R1? Apply operator K on VR1. Operator K rotates VR1 in anti-clockwise direction by 120. So it becomes K times VR1. How to write Y1 in terms of R1? Apply operator K on K VR1. Operator K rotates K VR1 in anti-clockwise direction by 120. How much you get? K square VR1. Now we have negative sequence components. So what about next negative sequence components? Almost similar definition to positive sequence components. They are equal in magnitude and displaced from each other by 120 degrees. With phase sequence not same, opposite. With phase sequence opposite to phase sequence of power system network. So power system network phase sequence is RYB. Opposite to that what you will have? RBY. Opposite to that what you will have? RBY. So it is VR2, VB2, VY2. And all have the equal magnitude. And they are displaced from each other by how much? 120 degrees. So how much Vy2 is? K times VR2. Vb2 how much? K square times VR2. Vb2 how much? K square times VR2. So this is regarding negative sequence components. So now you come across the third is zero sequence components. Third is zero sequence components. Positive sequence components phase same as the phase sequence of power system network. Negative sequence components phase opposite to phase sequence of power system network. Now is there any phase sequence left out? No phase sequence. So zero sequence components do not have phase sequence. So zero sequence components are equal in magnitude without any phase sequence. So you represent them just parallelly. R0, Y0, B0. All these three are equal. So now you replace this sequence components into 0, positive, negative only in terms of R phase. So what about this one? VR0, R1, R2. And similarly all these zero sequence components same as R0. What about y1? K square VR1. B1 K VR1. What about R2? I'm sorry, Y2 K times VR2. Next is B2 K square times VR2. So this is how you represent the three unbalanced voltages in terms of the three symmetrical components. In terms of three symmetrical components. So now we represent in the matrix form VR, Vy, Vb. Here VR0, VR1, VR2. First column is 1, first row also 1. Here K square K, here it is K square. Now the easiest way to remember this formula is, we have 1. So the power of K nearer to that is also 1. Here we have 2. Power of K nearer to that is also 2. That is the easiest way of remembering this formula. Similarly, you can write other way also. The sequence components VR0, VR1, VR2. How much? 1 by 3 times VR, Vy, Vb. First column 1, first row 1. Now interchange this K and K square. So here it is, represent the symmetrical components using this relation. So these two formulae are most important. These two matrices are most important, which you come across frequently in the next topics. Let it be fault analysis, both symmetrical fault analysis and symmetrical fault analysis. So these two matrices are most important. Continue with the next questions on symmetrical components. So these are asked in one of the GATE question papers. So you are having a delta connected load impedance, and where the open circuit has occurred in the phase C. Open circuit has occurred in the phase C. So you have to find the positive sequence current component in the phase A. So how to find out the positive sequence current component? IA1, you find in amperes 1/3 times IA plus KIB plus K square IC. How much IA? 10 at angle 0, KB 1 at angle 120, IB 10 at angle 180. Anyway, K square given 0, so no need to write K square value. So how much you get this IA1 in amperes now? On simplifying, 5.78 angle minus 30 degrees amperes. 5.78 angle is minus 30 degrees amperes. Now we solve this next question. A three-phase alternator generating unbalanced voltages is connected to an unbalanced load through a three-phase transmission line. The phase voltages of alternator are EA is 10 at angle 0, EB 10 at angle minus 90, ten at angle 120. So the positive sequence component of load current is so this is what you have to calculate here. In the figure, so we have to find out the positive sequence component. So IA1 per unit, how to write? 1/3 times IA plus KIB plus K square IC. But how to write what is this IA? You write it as EA by that corresponding reactance. Similarly, EB by the corresponding reactance. Similarly, EC by this corresponding reactance. So now you substitute the values. EA how much? 10 at angle 0. Total reactance J2. K is 1 at angle 120. EB 10 at angle minus 90. XB how much? J3. K square how much? 1 at angle 240. EC is 10 at angle 120. XC how much? J4. So we have to find this and check the values now. So all the values are given in amperes here. So these are in volts and ohms. As they are in volts and ohms, no need to specify in per unit. You will get the answer in amperes. So IA in amperes, IB amperes, IC in amperes. EA in volts, EB in volts, EC in volts. XC in ohms, XB in ohms, XA in ohms. So this is what we have to calculate. 3.15 minus 81 degrees amperes. So on simplifying, this is the answer you get for this question. Now you say some fault has occurred. When fault occurs, we have to check what will be the positive sequence voltage, negative sequence voltage, zero sequence voltage. Why you have to check? You know, when fault occurs, the system is unbalanced. And how you analyze an unbalanced system? Using symmetrical components, that is positive sequence, negative sequence, zero sequence. So find what are their corresponding generated EMFs. So now we have to check analysis of sequence generated EMFs during fault. Analysis of sequence generated EMFs during fault. Now for that, you consider that ER1, ER2, ER0 be the positive sequence, negative sequence, and zero sequence induced EMFs during fault. So how much ER1 per unit we have to check? Formula you know, 1 by 3 times ER plus EY plus EB. Now you have drawn earlier the phase sequence of a 3-phase power system network. There you have drawn with V, now you draw with E. ER, EY, EB. So what about EB now? K times ER. EY, K square times ER. So I am simplifying this one. EY how much? K square ER. EB, K times ER. You take out ER per unit as common. 1 plus K square plus K is 0. Now we have to find out ER2 per unit. So 1 by please I correct this formula here. ER plus what you write? K times EY plus K square times EB. Now how much EY is? K square ER. How much EB is? K times ER. Now if you take out ER common, 1 plus K cube, K cube. How much K cube is equal to 1. So on simplifying, how much you get? ER per unit. Now you know this formula of ER2. How to write ER plus K square EY plus K EB. EY how much? K square ER. EB how much? K times ER. So you take out ER per unit outside. 1 plus K power 4 plus K square. K power 4 is same as K. So 1 plus K square, how much? 0. Now what about ER naught per unit lastly? 1 by 3 ER plus EY plus EB. EY how much? How to write? K square ER. EB how much? K times ER. You take out ER common. How much? 1 plus K square plus K is 0. What is the value you get? 1 plus K square plus K equal to 0. Now check these 3 values here. Only positive sequence generated EMF is not 0. Negative sequence generated EMF 0. 0 sequence generated EMF is 0. That means you don't have a voltage source in negative sequence network and 0 sequence network. Important points. So in general, in positive sequence network, we draw voltage source. We don't draw the voltage sources in negative sequence network and zero sequence network. What is the reason? This is the proof for that. So, we have a voltage source in positive sequence network. How much? Equal to ER per unit. You don't have a voltage source in both negative sequence network and zero sequence network. So now we say that the positive sequence network has the voltage source ER per unit, and negative and zero sequence network do not have voltage sources. So this is the analysis of sequence generated EMFs during fault. We discuss the different methods connecting ground. The protection is by default connected in. You know that anyway in protection we come across that alternator windings which are by default connected in star are further connected to ground. So what are the different methods to connect the neutral and ground? So now we discuss the neutral, ground connections of an alternator. Or you represent directly all the star symbols, and here you represent ground. All these are the neutrals. Here you represent ground. Here also you represent ground. What is the first way you connect? Connect the neutral of alternator to ground directly. So what you call this method as solid neutral or the solid grounded. And say the current flowing how much? Some IN per unit. So what is the reactance offered? 0. And now further you connect the neutral and ground by means of a reactance. Say the current flowing is IN per unit. As neutral and ground are connected by reactance, you name it as what? Reactance neutral, or you name it as the reactance grounding. Now further, ground can be isolated from the neutral. That is, current do not flow from the ground to the neutral. So what will be the corresponding reactance? Infinite. This type of connection you name it as isolated grounding or isolated neutral. Isolated grounding or isolated neutral. So the neutral current flows from ground to neutral without any reactance, solid neutral or solid grounding, with a reactance Xn per unit connected between ground and neutral. Say reactance neutral or reactance grounding. When ground is isolated from the neutral, we say isolated neutral or isolated grounding. Now we check what is the per unit neutral current. First for case 1 balanced condition, case 2 unbalanced conditions. So it is the per unit neutral current. First it is case 1. Balanced conditions. So what is IN equal to? IR plus IY plus IB. You know balanced conditions, sum is 0. Now the case 2, unbalanced conditions. It is IR plus IY plus IB. Now when the system is unbalanced, how to analyze an unbalanced system? Using symmetrical components. So represent using symmetrical components. So how to write this one? IR naught plus IR1 plus IR2. What about this one? IY0 plus IY1 plus IY2. IB1 plus IB2. Now represent using 3 symmetrical components, that is, represent Y phase and B phase symmetrical components in terms of R phase symmetrical components. Now you represent R phase. IY1 is K square IR1. IY2 is K times IR2. B0 is IR0. K IR1. K square IR2. Now add this IR0s 3 times. So how much you get? 3 times IR0. You take out IR1 per unit common, 1 plus K square plus K, 0. And take out IR2 per unit common, 1 plus K square, 0. So how much you get? 3 IR0 per unit. So what is this IN per unit? 3 IR0 per unit. So where from this IR0 per unit, IN is IR0 per unit flowing? IN you check is flowing from ground to neutral. and this IN nothing but 3 IR naught per unit. So we say ground is the reference for zero sequence current flow. Ground is the reference for zero sequence current flow. Ground is the reference for which one? The zero sequence current flow. And what about positive sequence and negative sequence current flow? The reference is neutral. Neutral is the reference for positive and negative sequence current flow. That is, from ground to neutral, current flow is the positive sequence current. From the neutral onwards, we have the flow of positive sequence current and negative sequence current. Positive sequence current and negative sequence current. Now you have a break. First question is by Purushottam from Jaipur. Will you teach sag tension topic or not? See, sag tension is not in the syllabus of GATE examination, please. Next question is by Shailesh from Bikaner. The underground cables can also be located under the ice. Explain that how spacing between conductors affect corona. No, depending on the locality, you can have the underground cables underneath the ice also. But regarding the spacing between the conductors, suppose you consider a three-phase system here. And say, due to ionization of air particles, the free electrons collide the conductor surface here, and say it has collided the conductor surface here. So what happens due to that? The distance between the conductors also determines the corona, because if the conductors are in with close proximity, an arc is struck between the conductors. If they are separated by a very large distance, there is no formation of arc between the, say, R phase and Y phase conductors. Next question is by Arijit from Kolkata. Certainly, as a part of the topics in our syllabus, we have the discussion on all the topics, whatever you have quoted, and the transients on transmission line, doubling effect, short circuit current, DC offset current, and definitely we do more than 30-35 questions on these topics, the total fault analysis. Next question. Is by Arijit from Kolkata. Discuss short circuit studies. See, when I do the load flow analysis, firstly we discuss Y bus, then Z bus, use it for short circuit studies. Next question is by Arijit from Kolkata. Please teach sequence impedance of transmission lines and phase shift in star delta transformers. See, we have the sequence of the next topics, please. We do them in sequence. Next question is by Vishwam from Agartala. How can the phase sequence of positive and negative be the same? They are not same, please. They are only equal in magnitude. Positive sequence phase same as the phase of power system network. Negative sequence phase opposite to power system network phase. Next question is by Somdev from West Bengal. What is the equation for load current for negative and zero sequence component to find value from the figure? No, load current depends on what? Eg minus Vt divided by the reactance of the path. Next question is by Rachel. Show how Eg are different for different phases in unbalanced load. Now you got now unbalanced load. Eg will be same for unbalanced load for all phases. That is correct, but for that unbalanced load, you don't have the zero sequence source EMF, you don't have the negative sequence source EMF. But EGR, EGY, EGV will be same place. Always source is balanced, load is unbalanced. Whenever you say the system is unbalanced means Only load is unbalanced, source is always balanced. And unbalanced load depends on reactances or unbalanced currents. Reactances, please. Unbalanced currents depends on the reactances. Whether positive sequence reactance or negative sequence reactance or zero sequence reactance. Anyway, we discuss them in detail further. Next question is by Sanjog. When do we study about the transposition and double circuit lines? Again we come across them while doing the stability analysis, please. In the last week's session, you please refer 8 conditions. There the last 3 conditions or last 6 conditions are part of the double circuit line configurations also. So this is how you represent the per unit neutral current. Once you know the per unit neutral current, now we have to find out the per unit voltage to neutral. So now we have to calculate the per unit voltage to neutral, Vn per unit. So how to write what is Vn per unit? The neutral current multiplied with the neutral reactance. Neutral current 0, so Vn also 0. For unbalanced conditions, formula is the same. But how much Vn is? 3 IR naught. If you take out IR naught, how much you get? 3 Xn per unit. How much you get? 3 Xn per unit. These 2 lines are most important, please. If you write the reactance Xn, mention the zero sequence current 3 IR naught. If you write the zero sequence current IR naught, then mention the reactance 3 Xn per unit. So this is regarding per unit voltage to neutral. Now we check how to draw zero sequence networks of transformers. How to draw zero sequence networks of a transformer. Now you know that a transformer has primary winding, secondary winding, and either of the windings can be connected either in star or delta. So the windings of the transformer, that is primary or secondary, can be connected either in star or delta. So how you represent the basic configuration? Represent XT0 per unit. What is XT0 per unit? The zero sequence reactance in per unit of a transformer. Now it has both series switches and shunt switches. So now we discuss when you operate the series switches. So you operate the series switches when the windings are connected in star. You operate series switches when the windings are connected in star. Then what to do those series switches? Either you close or open. It depends on the neutral to ground connection. So whether you open the series switch or close the series switch, it depends on the neutral to ground connection. And suppose you have a solid neutral, what to do? Yes, neutral current flows from ground to neutral. Neutral current flows from ground to neutral. Or now you can represent with IR naught, because you are dealing with the zero sequence network of transformer. So mention IR naught per unit, the zero sequence current. Now check here, zero sequence current can flow from ground to neutral. There is a path for zero sequence current flow from ground to neutral. Now here also, when current can flow only when you close the switch. Here also, series switch, when current can flow only when you close the series switch. With how much reactance? With Xn per unit equal to 0. So for solid neutral, what you do now? You say that you close the series switch. With how much reactance? Solid neutral means Xn per unit 0, or you name it as fuse. Here IR naught per unit flows from ground to neutral. There is a path for zero sequence current flow from ground to neutral. Now here also, how current flows? Only when the switch is closed. With how much reactance? 3Xn per unit. So what you do now? You close the series switch with 3Xn per unit. Now here there is no zero sequence current flow flowing from ground to neutral. IR naught per unit 0 place. Zero sequence current do not flow. Here also, when zero sequence current cannot flow, only when the switch is opened. Only when the switch is opened. So for isolated grounding, what you do now? You mention that the series switch must be opened, because there is no path for flow of zero sequence current. Zero sequence current cannot flow. Here also, when zero sequence current cannot flow, when the series switch is opened. And similarly, we check the shunt switch. So when you operate the shunt switch, when the windings are connected in delta, you mention that shunt switch. For that, when to operate the shunt switch? When the windings are connected in delta. So what you do with the shunt switch, either open or close? You know the symbol of delta. Here you check, there is a closed path for the flow of current. So here also, when the zero sequence current flows, only when the shunt switch is closed. So whenever the windings are in delta, only one operation, you close the shunt switch. With how much reactance? Is there any reactance here? It is similar to this one, no reactance. With Xn per unit 0, or you say by means of a fuse. So this is how you connect transformer windings either in star and delta, and accordingly you operate the series switch and shunt switch. Now after the break we discuss all the 13 configurations of transformer connections. Okay, you have break now.